It's my great pleasure to introduce Chuang today as our speaker at the Virtual Informal Systems Seminar. Chuang got his PhD in Applied Mathematics at the University of Alberta in 2018, and then he was a postdoctoral fellow in the Math Biology MBO group at the University of Copenhagen. Following that, he had the distinction of being an Alexander von Humboldt postdoctoral fellow and Technical University Foundation fellow at the Technical University of Munich. He's currently an assistant professor in the Department of Mathematics of the University of Hawaiʻi at Mānoa, and the title of his talk is Mean Field Limit of Heterogeneous Networks. Chuang, the floor is yours without any further ado on my part.
Okay, thank you, Peter. Thanks a lot for your kind introduction, and many thanks for the organizer's invitation. So today's talk is about the mean field limit of heterogeneous networks. So this is the joint work with Professor Christian Kuehn at TU Munich when I was a postdoc there with him. So the outline is, well, first we'll talk about the outline of the talk. So first I will talk about heterogeneous networks are very popular, ubiquitous, or examples. And then we talk about why we care about heterogeneous networks, not just because it's popularity. And then
Excuse me, Chuang, we're getting some echo. I just wonder if we can fix that before
Should I probably move a little bit further, or is that possible now?
Yes, just try that. Let's just experiment with that.
Yeah, sure. Yep.
Okay,
and we talk about, oh, sorry, there's still echo, or
yeah, do you have another microphone on? Is there one and only one microphone?
I probably only have one, unfortunately, but let me try. Is that possible? I move it a little bit to some other place.
Feedback source?
Yeah, is that possible now, or better now, or it's still the same, or?
No, that sounds better to me. That sounds better to me.
That sounds better?
Yes.
Yeah, maybe probably position. Yeah, I'll probably can move the position. Yeah. Yeah, sorry for inconvenience. Could you hear better now, or?
It seems better to me now, yes.
Yes, the sound is better now.
And I should probably proceed.
Yes, please do. Thank you.
Okay, thank you. Yeah, thank you. Yeah, sorry for that. And then we're gonna move to why we want to study mean field limit and why it's generally difficult to study mean field limit of heterogeneous networks. I will talk about this via a Kuehn model network as an example. And then we move on to talk about briefly literature on mean field limit of heterogeneous networks from homogeneous to heterogeneous. And then we kind of propose or review the definitions for graph limits from different perspectives. And finally, we're going to discuss briefly about our main results and our contributions in comparison to the literature. And finally, I will just give a very brief outline of proofs depending on the time left and talk about some future topics. So throughout the talk, please feel free to let me know if I can make you understand. Thank you. So there are different types of network models in the real world applications, from the brain or neural networks to the social networks and ecological networks. We also have chemical reaction networks, which is a very popular topic now. And also we have a network of airlines connecting to different cities, like for instance, in US or Canada. And we also have a network over the computers where people play games on the computer. And we may also have a collaborative networks or a network of literature focusing on different research topics. And arguably, the largest one going to be the universe of all things, where everything is connected with each other. So we talk about a lot of network models, and one typical feature for the real-world applications, as pointed out by Lovas in his celebrated monograph, is that almost no networks are auto-coupled, or to say complete. So they all have heterogeneity. And for instance, if we consider the friendship network where every person have a very limited number of friends in comparison to the population on the Earth. So this network is local against well, globally sparse, obviously. And as I mentioned at the very beginning, we care about why we want to study heterogeneous networks, not only because it's popular, it's ubiquitous, but also because it could trigger new dynamics. For instance, remote networks can have sparsity-induced bifurcations. And the kind of general question that people all care about is how does the dynamics of the network depend on the heterogeneity of the network? So I'm going to use a very simple example, which is the chromotal network over a ring. So if we consider that we have a ring of oscillators, where each oscillator is only connected to its nearest neighbors, the forward one and also the backward one, and the form a ring. So if we have only 10 oscillators, we surely could simulate the oscillators or the network. What about from 10 to a million? So it may not be very handy to deal with the dynamics. So we ask, what is the dynamics of a typical oscillator on the network? Generally, it's very hard to track a dynamical system of very large size, no matter analytically or numerically. But one way to get around this typically is to find a simplified mathematical object to work with. For instance, what if we ask the following question by looking at the dynamics of a simplified model as the limit, so as n the number of nodes or the number of total the total number of oscillators on the ring. So what is the asymptotic dynamics of the typical oscillator on the network? Generally, we'll do the following. So we first sample the dynamics of each oscillator independently, and then we obtain the so-called empirical distribution. So we put a Dirac measure on each oscillator, and then we give the equal weight to each Dirac measure, and we get the empirical distribution. So we ask whether, and now we have a sequence of empirical distributions indexed by the number of nodes. So if the sequence has a certain limit in some weak or distributional sense, we call this the mean field limit. But why generally to study mean field limit of heterogeneous networks is very difficult, because basically there are two limits. One is you have a limit of networks, and the other one is that you have a limit of a sequence of underlying graphs. So first, to make the question well-defined in the sense of mean field limits, we might be able to ask, what is the limit for a sequence of graphs or networks? And of course, that depends on how we define the limit of a graph sequence. So next, I'm gonna briefly mention and compare the results in mean field limits of networks as far as I know on graph limits. So from the Hab, Russian and Neunzert in the 1980s around, they derived mean field limits with a physical background for homogeneous networks. And until 2014 or 2018, Medvedev and his collaborators used the very novel idea of proposing fiberized mean field limits. And I just want to emphasize that it seems that many of other other literature afterwards really benefit from this idea which makes it possible to discuss meaningful limits from homogeneous networks to heterogeneous networks using the fiber idea. And this not only influences the network, the works in deterministic regime, which was discussed in his paper in 2018, but also later on in stochastic regime. And of course, there are interesting topics discussed by Peter Chuang and also your collaborators and Dr. Ming Huang. And you talk about graphon game theory as well. And also, I'm very interested and happy to know that your recent works on extending the ideal of graphon to graphixon and vertexon. And there are also other related works on meaningful limits in the stochastic regime. For instance, people discuss the chromotal networks on the sparse graph limits in the sense of the Benjaminian and the Schramm. And there are also works by sorry, probably failed to pronounce it correctly, the three authors, Baraka and Record. Not sure whether I can move it. Oh, yeah. Bati and Wu, where they discuss the graphon stochastic game. Seems also the kind of the first few works, at least, where people introduce the ideal of graphon to discuss dynamical systems and dynamics involved, induced in terms of by the graphon limits. And Kuehn seems the first to kind of employ the operator viewpoint from the paper, and well, I think online in 2020, to introduce the ideal of graph operators, the so-called Graph, into studying dynamical systems. And this is kind of a general extension of graphon. So later on with his PhD student, they used the graph operators to study chromotal type networks. And we further make slight extensions of the work by Kaluginski and Medvedev in 2018. Basically, we we provide a new viewpoint of looking at graph limits. And I'm going to talk about that a bit later. And Jabin, Payato, and Solar in 2020, almost the end of the year, where they have their very interesting and elegant work on sparse networks of linear dynamics, and with the coupling, with the kind of linear, well, not linear coupling, but the nonlinear function where the argument is the difference of two phases of the oscillator. I'm sorry for typo here. And basically without any technical conditions on the regularity of the graph, where they only assume that the graph is sparse. And later on, we also kind of extend the mean field limits of heterogeneous networks by considering when the underlying graphs are dynamic and co-evolve with the dynamics on the graph, as well as we consider networks of higher order interactions, roughly saying that we consider the Vlasov equations on hypergraph limits. So next I will talk about, well, briefly kind of review. I'm not sure whether we could just skip this part a little bit, because I know that everyone is expert on at least applying graphons already. So we just briefly mention it a little bit in case someone may not be familiar in the audience. So we want to talk about the idea of looking at a sequence of graphs and try to characterize the limits. So as when we go back to the very original question that we asked, why it's difficult to study many field limits of heterogeneous networks, simply because there are two limits concepts. One is for the sequence of graphs, and the other one is for the limit of the networks or dynamical systems. So the first one is we want to define what is the limit of a sequence of graphs. Is that still a graph, or what it could be? So by increasing the number of nodes, gradually one could get a sequence of graphs. And let me just recall several perspectives to view a graph. So first is, excuse me. So first is the already very popular one, the so-called graphon, where people perceive graph as a function defined on the product space. Whereas you could think about this as the generalization of the space for vertices. And then they consider graphon as a integrable measurable function defined on x squared with respect to certain reference measures. For instance, let's say the big measure. And there's also the Benjamin-Schramm limit, representing the limit of sparse graphs, where the viewpoint is more combinatorial and graphical. And we also have the Graph perspective, meaning that we regard a graph limit object as a positive linear operator. So from one into LP space to another LQ space. And as I said, feel free to interrupt me if I cannot make myself understood. So there are different advantages and disadvantages for these types of generalizations. For instance, although graphon is good in the sense that it could be analytical, but it cannot characterize graphs which are not dense. For instance, if we consider the limit of a sequence of rings. The second, for B, which is the Benjamin-Schramm limit, although it could characterize the sparse graph. And since this is a more combinatorial way, it may not be as handy as graphon to be used in dynamical system analysis. And finally, the graph operator does provide a way to unify graph limits of different densities. So it could be dense, it could be sparse or intermediate density. But there's a subtle issue about the convergence. So when we talk about the convergence, and in the sense that we regard the graph limits as operators, we basically use the so-called action convergence coming from the paper in 2020. But for that convergence, if you want to use a metric that induce that convergence, generally the metric is not very handy to use in the analysis, for instance, establishing estimates for the dynamical systems. So there are several kind of typical network structures where likely not dense, obviously not dense graphs. For instance, you consider a ring network, or you consider a tree network, or you have a ring of clicks where each click representing a complete subgraph. For instance, in the last figure here, we have a ring of clicks of 3 nodes. For each node in red, connect to other nodes so that it form a small complete graph of node 3. And we also have a hub network where we only have a hub and all the rest nodes only connecting to this hub. So it's pretty sparse except one node. And for these networks, generally, or graphs, generally, one cannot apply graphon to study the limits. And also, for instance, let me just pick the example from the paper I think by the two graphists in 2020, where they propose the so-called spherical graph. So consider now we have a sphere. We'll pick a point on the sphere, and we regard every point on the sphere a generalized vertex or node. And this node only connects to all the points lie on the circle, which is perpendicular to OX, where O is the center. And we denote the set of perpendicular points as the X perp. So this gives you the idea that there are certain type of graph limits which are neither dense nor sparse like the graphing, where you only have a uniform bounded number of uniformly bounded degree for each node of the graph. And just to review a little bit, what is the definition for a graphon? So basically, or how to represent a finite graph in terms of a graphon. So for instance, we take a very simple example here where we have only 4 nodes, where 1 is connected to 2 and 4, 2 is connected to 4, 3 is also connected to 2 and 4. So first, we could write up the adjacency matrix associated to this finite graph. And then we get and using this matrix, we could define a function over the x squared, where x is the unit cube. The x is the unit interval from 0 to 1. And we just color, and we first do a equipartition of the entire product space. For instance, here we have only 4 nodes. So we have a partition into 4 subintervals for each interval from each unit interval from 0 to 1. So since 1 is connected to 2 and 4, so that means we have 1 is connected to 2 and 4. So we color these 2 small blocks in black color, and the rest zeros we use the white. And in this way, we have a colored or in black and white figure or graph associated to this graph. And then we interpret this graph as a function defined on x squared. So we put 1 over the region where it is colored black and 0, 1, it is white. And so that we get a piecewise defined step function. So as we said, there are dense sequence of graphs. There are also sparse sequence of graphs. And by saying dense or sparse, we refer to the number of or the number of neighbors for each node, or to say the degree of each node. If the sequence of graphs and the degree for each node grows like O of n, where n is the total number of nodes for the graph, and then this is a dense graph. Otherwise, well, not otherwise. The other situation is that when the sequence of graph is sparse, meaning that the degree of the node grows uniformly boundedly, independent of the number of total nodes in the graph, as the number goes to infinity. So we know that graphon is appropriate in representing limits of dense sequence of graphs, but it may not be appropriate to characterize the sparse sequence, say, for rings. Why this is the case? We just use ring as the example to illustrate this point. So with the proper scale for a non-vanishing norm, if we still represent the finite graph, which is a ring, as in terms of a graphical representation, we can have the graphical figure for this graphon look like this, where saying the small dots in black represent we assign a value 1 there, and otherwise it's 0. And as we increase the number of nodes where get finer and finer equipartition of the interval from 0 to 1, we try to have the limit. So we wonder if we represent the ring as the graphon, what we get for that limit. Well, the limit could either be trivially 0 when the graphs are endowed without enough weight or scale, when the scale is into the power alpha with alpha less than 1 over p. Or it doesn't exist because we kind of normalize the LP norm of the graphon so that the LP norm of all these finite graphs or S rings are 2 to the power 1 over p. And in this case, we have no limit in the LP space for the sequence of rings. So that's why it's improper to use graphon to characterize the limit object of a sequence of sparse graphs. And how could we kind of get around or overcome this difficulty? For instance, how to represent a sparse graph limit analytically, where we try to use the so-called digraph measure as we name it, or essentially we use measure-valued functions to represent the graph limits. So if you consider that we have a space of vertices, which is x, you could imagine x as the unit interval from 0 to 1. And in certain cases, it may not be proper always use 0 to 1, for instance, for the rings. Because if you still remember, if we have 10 nodes from 1 up to 10, so 1 is connected to 2, but also connected to 10. So that means we kind of merge the the starting point and also the ending point. So it's better in that case that we use the circle to represent the space of vertices. So X could be arbitrary finite set in the Euclidean space of finite dimension, of course. And the M sub plus of X representing the space of positive finite measures. So roughly saying that a so-called digraph measure is a measure-valued function defined on the space of vertices X with the function value taken from as a finite positive measure. And we call it a Graphon as long as this is symmetric in the following sense. So saying that if you regard this measure-valued function as a measure over the product space of X times X by assigning a reference measure, for instance, the mu sub X, and then you get the direct product of these two measures to cook up a measure over the product space. And as long as this product measure or measure over the product space is symmetric, we call it a Graphon. So in this way, we kind of represent Graphon in terms of measure-valued functions. And the motivation of doing this is not for fancy purpose, but rather because of the analysis in applying the generalized graph limits into the dynamical system setup when we try to derive the mean field limits. And similarly, if we consider this measure-valued function, where at each point we take an absolutely continuous measure with respect to this reference measure mu x. You could think about this mu x, for instance, as the Lebesgue measure, but not necessarily the Lebesgue measure over x. It could be a little bit ugly ones. For instance, you could also take this as the Cantor measure over 0, 1. And in doing so, we associate each so-called absolutely continuous measure-valued function, or the DGM, to a graphon. Well, how to define the graphon? Well, simply we just take the density over the product space, and then you derive the integrable function over the product space x squared, and that's the classical definition of graphon. So in this way, we kind of use the so-called DGM to cover not only the graphons, but also, well, roughly saying is kind of equivalent to graph hops, but the metric or the convergence will be different from graph hops or graphon. So up to here, may I know whether there are any questions or clear?
Any,
Okay,
yes, maybe. Yes, thank you. Can I just ask, like, how
Sure.
do you, any intuition on choosing the reference measure mu x?
Sorry, intuition or
Should,
I would just illustrate the examples shortly. as
okay.
well. Sure.
Thank you.
So actually, I just want to say that this kind of new perspective to give you a new perspective representing the graph limits. So we do see the graph limits as measure valued functions. And the kind of difference that I'm going to also emphasize probably later is that we here use the bounded Lipschitz metric to measure not only for mean field limits in the applications, but also for the graph limits. In contrast to the cut metric or the cut norm that people generally use for graphons. And here you could understand this function as every time we pick a vertex and we get a value we get a function value evaluated at the point x, you could think about this or a so-called fiber measure as representing the information of the neighborhood of node x. So if it's a discrete measure, you could think about this, it precisely captures the weights of the neighbors of the node x. So it could be, so in that case, it's a vector. So let me just go back to the example like the rings. So if we consider the rings, and now we use the underlying space of vertices as the circle. So you could imagine that we have a ring, and we put more and more nodes on the ring, and so that the ring becomes denser and denser, and finally it's actually become a circle. And every point you could think about this as an abstract node. And what is the limit of the rings? In this case, we could simply get the limit, and that limit is nothing but 2 times the Dirac measure sitting at every node x. The reason or kind of intuition behind is that you think about the every node is only connecting to the nearest neighbors, the forward and the backward. But as you get finer and finer partition, these 2 nodes connecting to x are going to be closer and closer to x, and eventually they squeeze together. So an example here. Sorry.
Can I jump in for a question? So here
Sure.
in the limit in the previous slides, then one cannot distinguish a graph which is a ring with a graph that is self loops, whereas the loops is like 2 multi-edge, right? In the limit.
Yes. I think the idea here is that we so far have a way of characterizing like the graph limit objects.
Mm-hmm.
Whether there will be different representations, or to say whether you have a 2 sequence of finite graphs that could approximate the same graph limit object, that's possible. So this is something that you, as you mentioned, yeah, of course, you cannot distinguish these 2 sequences because they converge to the same point. But this also happens like even for real numbers, right? If you consider 1/n as a sequence, you have 1/n squared also has a sequence. You cannot distinguish these 2 because as the neighborhood nodes goes to infinity or the index goes to infinity, these 2 sequences are approaching each other. Actually, they all also approach to the same limit. So you can, in that sense, you cannot distinguish these 2 sequences. Yeah.
Thank you.
Yeah,
May I also jump in? I'm sorry.
Sure.
Yes. And is this limit unique in the sense that I do not understand why the coefficient must be 2?
Yeah, the 2, as I said, if you consider the ring, every node is connected to only 2 neighbors.
Yes,
That's why you have a 2 there. Yes.
but when they come together, you could
Yeah,
think
when
of them as just one big Dirac.
No, it's just because you have to count the degree. Like, for instance,
Okay.
so here we have one node connected to it. We have one direct measure because that represents the node connecting to one neighbor. But
Okay.
now for every node we have 2. So that's why there's a 2 there.
Okay, so that constant takes tracks of the degrees.
Yeah, basically. Yeah, exactly.
Thank you.
Yeah, thank you for the good question. Yeah. Right. So we could also consider the circle graph. This kind of similar situation as the spherical graph. So for the spherical graph, basically saying that you consider this a sphere, and now you consider a circle. If you consider the circle, I'm not sure where. Yeah, I do have a figure here, but it's not the kind of geometric one. So, sorry, you could, for instance, consider that you imagine you have a circle in your mind, and you pick an arbitrary point on the circle, and this point it only connects to 2 neighbors. Sorry, only connects to 2 points that is also perpendicular to that. So think about that. We have a node here and to connect to the center to get the line. We only have, and we have a perpendicular line through the center. This is a diameter, and this diameter go through the center and connecting to only 2 points on the circle, and that point only connecting to these 2 points. Yeah, I should have a figure here, and in that sense, for instance, we consider this limit. And to put a 0 here, for instance, 0 as one of the node on the circle. And it only connects to the other points. And the other points are nothing but, in this case, is 1/4 and 3/4. And by saying that, we identify the unit circle to the 0, 1 via the natural embedding. And similarly, if you choose the point to be 1/4 and you're connecting to 1/2 and also 1, or to say 0, because 0 and 1 are identified to be the same point in this case. And you could just move on. So basically saying that every point is connecting to other points. And if you draw the figure, you actually see that these are just perpendicular line, parallel lines. And the other example here that I provide is, once you see this figure, you kind of have an intuition is that if you consider the horizontal line as the space of vertices and the vertical line as the measure valued function, and every time you pick a point in X, the space of vertices, you associate it with a measure on X. So if you continuously change this measure, you actually get a parametrized family of measures, and you can make this as a smooth curve in the space of finite positive measures. But in this case, I just want to illustrate that by defining limits in terms of a measure valued function, you could cook up with a variety of different examples. For instance, here, we could consider that we have a graph limit, or the so-called digraph measure, where every time you pick up one point between 0 to 1/3, you get a uniform measure over this interval. And this interval is from 3/2 to 1 minus 3/2. And between 1/3 to 2/3, you put a Digraph measure there. And from 3/2 to 1, you get another uniform measure over the over another interval, which is 3/2 times 1 minus x to 1 minus this number. So basically representing this segment here. And you could have a so-called digraph measure. And in this way, I do appreciate that, Peter, that you send me your interesting work to me and to kind of get the motivation that you might be interested in. So that's why I put an example here to see whether it might be interesting to many of you or some of you here. For instance, for this measure, you could just define the derivative of this measure valued function with respect to the node x in the following way. For instance, well, the limit, the derivative is to say that you have a difference between two measures with the independent variable close to each other. One is x plus h, the other one is x. You think about the capital X here as just the unit interval from 0 to 1.
Right.
And now the eta x plus h, I guess I put it to be the superscript here as a measure. And the other measure is eta x. So these two measures are finite positive measures. By subtraction, it means we get a signed measure. So this is a well-defined object in the space of finite signed measures. And it divided by h means that you scale the mass of the signed measure. So this is still a signed measure. So if the limit as h goes to 0 exists, means this is a object in the space of finite measures, but signed measures. If the limit exists, we define this as the derivative of the measure valued function with respect to the vertex x evaluated at a point. And in doing this, for the specific example here, we could directly calculate what is that. So this is precisely the derivative for this specific DGM or digraph measure. Yeah. And similarly, the other way of proving this is, for instance, we have a given measure mu, which is a specific measure on the in the space of finite positive measures. And we multiply this by a function of x. And the function of x, you could make it as smooth as possible. And then you differentiate it using the same definition in the previous slide. You could actually calculate the derivative. But here, since we could, for instance, consider x not necessarily to be a one-dimensional object, which is the unit interval, you could also consider it as a cube, as you proposed in a paper. For instance, you embed it in the Rm, in the Euclidean space of dimension m. You could choose m to be 2 or to be arbitrary number here, and then get a partial derivatives. You get a gradient too. And this is nothing but you only deal with the partial derivatives or gradient of f, or divergence of f, and then multiply by this measure. Yeah. And I just want to, sorry, I just want to, I want to run over time. Oh, sorry, I guess I'll already run almost over time. So I just quickly wrap up the talk. And so this table kind of lists different type of networks as illustrated as examples, like you consider the ring, the star, or binary tree, or click, a ring of clicks in whatever way. You could represent them as a graphon, but you could also represent them as a DGM, or digraph measure. And the different ways, they have different representations, but they will have different use when you talk about their limits. And I may not have time to discuss further about all these things. If you are interested, maybe you can also refer to my paper, table paper. They're all listed there. So I just want to briefly mention probably the results as well. The main results, we basically have 3 assumptions. One is we have a local Lipschitz vector field and a nonlinear coupling function. The second one is the vector field. So just this is in comparison with results in the literature, where generally the vector field is assumed to be uniform Lipschitz, but not just local Lipschitz. And the second one is that we assume you get a dynamical system. So as long as the dynamical system has a compact invariant, positively invariant region, meaning that you could use the Nagumo subtangentiality condition to construct such invariant, compact invariant region, and you're good to use the results here. And this is in contrast to most results where they consider the underlying phase space is compact. For instance, chromato networks on a circle or just on a higher dimensional torus. And the underlying digraph measure or graphon, measure valued function here is bounded only for is already sufficient when we want to derive the well-posedness of the Vlasov type PDE. So this is kind of the well-posedness that we derive for the Vlasov equation, or to say the equation for the mean-field limit, meaning that we do not need any requirement for the regularity of the digraph measure. We only need the boundedness there. But for the approximation, we do need the continuity, meaning that we require the measure valued function to be continuous. And you could have discontinuity up to a finite number, and you still can derive similar results here, meaning that you still have the convergence or approximation in terms of a discretized ODE system as a network to approximate the mean-field limit using the empirical distributions. Maybe I think something kind of as a comparison might be interesting a little bit. So in comparison to these works in the literature where people consider no matter a deterministic regime by Medivh and his collaborators, and also the three authors where they consider stochastic graphon systems. You definitely already familiar, more than familiar than me. And also, there are also recent works by Kuehn, one of the speakers also here invited in 2020. They all use the fiberized way of characterizing the mean-field limits, and basically saying that they either require like the phase space to be compact, or they of course technically might use not necessarily compactness of the phase space, but rather the uniform boundedness of some moments of the solutions in a stochastic regime. But rather saying that in our context, we do not require the global Lipschitz continuity for no matter the vector field or the nonlinear coupling here. And the graphon, as I illustrated here, it could represent the the DGMs are not necessarily dense. Specifically, the graphons are just the special cases when the DGM are take the absolutely continuous measures as its function values. So it could be dense, it could be sparse, and could be of intermediate densities. But of course, there are also other cases where our framework cannot cover, for instance, if we lose the continuity in some sense. And also the other thing I guess I want to mention is that the difference is in here, we use the consistent metric, not only for the mean-field limit as well together with the empirical distributions, but also for the graphon, for the graph limits. So we have the sequence of graphs, we have the sequence of dynamical systems, and generated by the generating the empirical distributions. We use the same metric, which is the bounded Lipschitz metric, or the Kantorovich-Rubinstein Wasserstein metric. So we don't use the K norm here for the graph limits. And another difference from the paper by Medivh and also Wu et al. Is that we allow the fiberized mean-field limit not necessarily to be a probability. You take every point as a vertex, you have a distribution, but that distribution may not necessarily be a probability, meaning that you may not have the normalization for each fiber, but rather you consider the integration over all the vertices. You cook up that integrated measure over only on a space of y, where y is just the phase space, and that is a probability measure. And by doing this, we actually allow that the fiber measures for some bases or vertices, it could be fatter, and for others, it could be thinner, but not necessarily saying that they have the same shape. And another interesting observation in comparison to the results here is that in the papers listed here, the continuity of graph limit is not necessary for well-posedness. And this is the same case as we did in our paper. So the continuity or regularity basically for graph limits is only used when we derive the approximation of the MFL limit. And technically, in this literature where people use the idea to approximate the graph limit, basically they regard the graphon as an integral function, and they use the step function to approximate the integral function. And this is the idea behind. And why we could do something a little bit general is simply because we use a different approach to deal with the approximation. So we use the recent results, one coming from my PhD thesis, and the other one is generalization of our result from 1D to higher D, is to approximate a general probability measure in terms of empirical measure with finite support, where on each atom of the approximation, you have equal math. And using that result, we don't care whether the fiber probability measure or just measure is absolutely continuous or not absolutely continuous. Yeah, I guess I'm sorry that I didn't control well the time. I guess you probably just need to close it in 1 minute or so. So this is kind of a schematic diagram for the approximation. You basically consider if this is a graph, the x is the space of vertices and m of x is the other axis, and you could still use kind of the stepwise functions to approximate this function, but values are not real. Instead they are measure valued functions. So there are different types of applications coming from epidemiology, ecology, and also social sciences. And I will be also happy to see if there is any possibility to be applied to game theory too. And for the topics here, for instance, we haven't talked about like the calculus of these digraph measures, and it will be potentially interesting, I guess, to Peter and collaborators here. And maybe we also like to extend results, not necessarily including continuity, but rather saying that we define more generally, like whether we could talk about the integrable measures. And of course, it will be interesting to discuss like the evolution of the digraph measures only, where you allow these graphs to evolve. And this is kind of also related to our work on the MFL limit of adaptive networks. And hopefully, for instance, the games on the smooth digraph measures might be interesting to some of you here. Yeah. And that's something that I think I want to talk about, and I will be happy to take questions from you. Thank you.